Now, for representations, there are two major ones. So, again, I suspect you've all seen this before, but let me remind you. One way to represent a graph and the edges is via a matrix, an adjacency matrix. So here we represent G. I'm going to give the definition for undirected graphs, in which case this is a 0, 1 matrix. Directed graphs, it's the same, it's just you have zeros, plus ones, and minus ones, with a plus or minus 1 explaining the orientation of the edge. But for the undirected case, we use an n by n matrix, which is 0, 1. Where a given entry of the matrix is 1, if and only if. So remember, it's n by n. Okay, so an entry is indexed by two nodes, I and j, and it's a 1 if and only if there's an edge between the nodes I and j. Okay? So G has an ij edge. All right? So throughout the course, we're not going to talk a ton about space complexity, but it's worth talking about it for graph representations. So what would be the space of the adjacency matrix representation as a function of n and m? How many sort of bits are you going to need to represent a graph in this way? N squared. Good. So no matter what the density m is, basically it's an n by n matrix. Okay, so it's n squared space. The constants are quite small, right? You only have to store 1 bit for each potential edge. But in general, unless you do some extra tricks, it will be quadratic in the number of nodes. So that's the adjacency matrix. There's also the adjacency list, where instead of a matrix, you use two arrays, or two linked lists, which are hooked to each other, sort of point back and forth from each other. So the ingredients are as follows. There's an array of vertices, or a linked list if you prefer, an array of edges, and then these two arrays are wired back and forth to each other. Specifically, each edge points to both of its endpoints. And each vertex points to all of the incident edges. Okay, so people point to their neighbors sort of in the way you'd expect. So let's do a space analysis here. Array of vertices. How much is that going to take? Right, theta of n, kind of almost by definition. Similarly, the array of edges is going to be theta of m, the number of edges. How about the pointers from the total space complexity of the pointers that go from an edge to the incident endpoints? What's that going to be? So what is it per edge? It's constant, right? So there's just 2 pointers, and then there's m edges. Okay, so it's constant space per edge. So overall, this is going to contribute theta of m to the data structure. Now here's the only slightly tricky one. How about this last set of pointers? Okay, each node points to the incident edges. What's the total space there? Right, so one way to think about it is that you only need n per vertex. That's the largest number of neighbors a vertex might have. That would give us a bound of n squared. We can actually do better. It's the same as the number of edges. So that's good. So if you think about it, each pointer in this set is just the reversal of a pointer in this set. Right? So basically each node has to keep track of the incident edges. Each of those edges is pointing to it, and it's just pointing right back. Okay? So the number of pointers in the last group is exactly the same as the number of pointers in this group. So this is also going to be theta of m. Okay? So total theta of n plus m. All right? And again, so I'm writing n plus m. Again, in sort of in the common case, more or less, when we're thinking about m as being at least as big as n, I could write m here. Right? So n would be sort of a lower order or a constant term if m is at least n. But in general, this is what I'm going to write, okay, if I'm not making the assumption that the graph is connected. Okay? So the constants here are going to be bigger because you're storing pointers instead of just bits. But for sparse graphs, this is going to be a much smaller space complexity, right? So remember, in a sparse graph, m is something like linear in n, and then here you're linear in n, and here you're quadratic in n. Okay? So both of these representation schemes are important and used in practice. As a computer scientist, you should be familiar with both. It turns out that in this class, we're pretty much only going to use the second one, okay? So we're pretty much only going to be talking about algorithms that use adjacency lists. The main reason for that is just because of the choice of graph problems that I've chosen to study, that we're going to choose to study in this quarter. They mostly have a graph search flavor. And if you think about it, the adjacency lists are particularly well suited for searching algorithms. Okay? Another reason why it doesn't bother me that we focus more on adjacency lists is, especially as time goes on, the networks, the types of graphs we're interested in the 21st century, they tend to be both big and sparse. So if you take like the web graph or something like that, I don't know if anyone knows what the current size is, but I don't even know good estimates on the current size. But a conservative lower bound would be, if you have a node for every web page, you're certainly at least 10 billion, probably much more than that. So that's 10 to the 10. So then, when you're talking about n squared space, you're talking about 10 to the 20. And that's really, basically, even with current technology on a lot of engineering, that's too much to handle, 10 to the 20. On the other hand, the average number of edges at a given node in the web graph is going to be something more like 10. Okay, so it is going to be very sparse, the number of edges. It will be larger than the number of nodes, but maybe by one order of magnitude. Okay, so this n plus m is going to be something like 10 to the 11, which is way, way, way better than 10 to the 20. Okay, and that's pretty typical of modern networks that we like to think about. They tend to be pretty sparse. You could have sort of sparse versions of the adjacency matrix representation, but sort of with no thinking whatsoever. If you use an adjacency list, it'll automatically tune itself to be small space if your network happens to be sparse. So that's another reason to talk about them. Okay. Questions thus far?
For the adjacency matrix, if we have a directed graph, does the diagonal have to be 0?
Yeah, unless you allow self loops. But we're not going to talk about self. You can node point to itself. Yeah. There are some applications where that's useful, but not in the ones we'll talk about.
How do you represent that?
On the diagonal? Yeah. Anything. You just put a 1, say. Other questions? Yeah.
So in the adjacency list, why don't you only use array of vertices and let each vertex point to infinite vertices? Why do you need an array of edges?
So because you want to be given an edge, you want to sort of know what the two endpoints are. So in particular, you might want to. So the question is, why not just have the array of vertices and sort of directly wire them up to each other? The main reason is because you often want to annotate the edges of a network with information. So like when we talk about Dijkstra's algorithm, each edge will have a length, for example. So I think if you didn't want to do too much with your network, I think, and it wasn't very dynamic, you could get away with that kind of data structure. In general, this is what's natural, because edges are really conceptually a first-order entity that could be labeled with additional fields. So typically when you program up graphs, you explicitly have structs for the edges. It's a good question.